Title: Recurrence Relations, Decoding Algorithm Efficiency. Today, I am going to discuss one of the most important concepts in algorithm analysis, recurrence relations, and how they help us understand the efficiency of recursive algorithms. Whenever an algorithm calls itself recursively, determining its running time becomes difficult using ordinary mathematical formulas. Instead, we express the running time in terms of the running time of smaller subproblems. This mathematical expression is called a recurrence relation. Throughout this presentation, we will explore what recurrence relations are, why they are essential in computer science, different methods to solve them, the Master Theorem, characteristic equations, famous recurrence-based sequences, and finally, how to choose the appropriate solving technique. By the end of this presentation, you will be able to analyze recursive algorithms systematically and predict their computational complexity before implementing them. Title: The Hidden Cost of Recursion. Before learning recurrence relations, let us first understand why recursion introduces hidden computational costs. The first point is self-referential runtime. Unlike iterative algorithms, recursive algorithms define their running time using their own previous executions. For example, when merge sort processes an array of size n, it first sorts to smaller arrays and then combines them. Therefore, its running time depends on solving smaller versions of the same problem. The second point is divide and chip strategies. Many recursive algorithms follow one of these two approaches. In divide and conquer, the problem is split into several independent subproblems. In chip and conquer, the problem size is reduced gradually, usually by one element or one constant amount. Finally, consider stack frame overhead. Every recursive function call creates a new stack frame in memory. This stack frame stores function parameters, local variables, and return addresses. Although each frame may require only a small amount of memory, thousands of recursive calls can significantly increase memory usage. Therefore, when analyzing recursive algorithms, we must consider not only the mathematical recurrence but also the overhead introduced by recursion itself. Title: The Two Pillars of Recurrence. Most recursive algorithms belong to one of two major categories. The first is divide and conquer. Here, the original problem is divided into multiple smaller subproblems of equal size. Each subproblem is solved independently, and their results are combined. Examples include merge sort, binary search, quick sort. For example, merge sort divides an array into two halves repeatedly until each subarray contains only one element. The second strategy is chip and conquer. Instead of splitting the problem, the algorithm removes or processes one element at a time. Examples include factorial, linear search, recursive insertion sort. The recursion depth here is usually proportional to the input size. One important concept is the base case. Every recursive algorithm must eventually stop. Without a base case, recursion continues forever, leading to a stack overflow error. Thus, every recurrence consists. Title: Method 1, the substitution guess. Our first technique for solving recurrence relations is called the substitution method, also known as the guess and prove method. The first step is to make an educated guess about the complexity. For example, suppose we guess that the recurrence grows as O n log n. The second step is to substitute this guess back into the recurrence equation. Then, using mathematical induction, we verify whether our assumption is correct. If the assumption satisfies the recurrence, our proof is complete. However, choosing the correct guess requires experience. Often, we examine small input values or draw a recursion tree to identify patterns before making the guess. This method is extremely powerful because it can solve recurrence relations that cannot be handled directly using the master theorem. Title Method 2, the tree method. The second technique is the recursion tree method. Instead of solving equations directly, we visualize the recursive calls as a tree. Each node represents one recursive function call. The root corresponds to t, n. Its children represent recursive calls on smaller inputs. The first step is to draw the recursion tree. Next, determine the height of the tree. For divide and conquer algorithms, the height is usually log n. For chip and conquer algorithms, the height is usually n. Finally, calculate the work performed at each level and sum all levels together. This graphical method provides excellent intuition about how recursive work accumulates. It is especially useful when the recurrence does not fit standard mathematical formulas. Title: The Master Theorem Revealed. One of the greatest tools in algorithm analysis is the master theorem. It quickly solves recurrence relations of the form T n is equal to at nb plus f n. Here, A represents the number of recursive calls. B is the reduction factor. And f n represents the work performed outside recursion. The theorem compares recursive work with non-recursive work. There are three cases. Case 1. If recursive work dominates, then the complexity becomes theta of n raised to log base b of a. Case 2. If recursive work and extra work are balanced, then the answer becomes theta of n raised to log base b of a multiplied by log n. Case 3. If the non-recursive work dominates, then the complexity is simply theta of f n. The master theorem saves enormous time. Title: Characteristic equations. Some recurrence relations cannot be solved using the master theorem. For linear homogeneous recurrences, we use characteristic equations. Consider the recurrence T n equals C1 multiplied by T n1 plus C2 multiplied by T n2. The first step is to assume the solution has the form T n equals r raised to n. Substituting this assumption transforms the recurrence into a polynomial equation. This polynomial is called the characteristic equation. Next, solve for its roots. Finally, construct the general solution based on these roots. If the roots are distinct, the solution becomes a combination of exponential terms. If roots repeat, polynomial terms are added. This technique is widely used in Fibonacci sequences, linear recurrences, signal processing, and discrete mathematics. Title: Famous Sequences, Fibonacci and Beyond. Many famous mathematical sequences arise naturally from recurrence relations. The first is the Fibonacci sequence. Each number equals the sum of the previous two numbers. Its recurrence is Fn equals Fn1 plus Fn2. Its growth rate is approximately proportional to the golden ratio raised to n. The second example is Catalan numbers. Catalan numbers appear in many combinatorial problems. They count binary search trees, balanced parentheses, polygon triangulations, expression parsing, dynamic programming structures. The third example is factorial. Its recurrence is n factorial equals n multiplied by n1 factorial. Title: Strategic choice of technique. Not every recurrence should be solved using the same method. Choosing the correct technique makes analysis much easier. For small linear recurrences, use iteration, characteristic equations. For divide and conquer algorithms, the master theorem is usually the fastest solution. For unusual or irregular recurrences that do not fit standard forms, use recursion trees. Substitution method. Therefore, before attempting to solve any recurrence, first identify its structure. Recognizing the recurrence type often determines the best solving strategy. Title: Master the complexity. To conclude, recurrence relations provide a mathematical framework for understanding recursive algorithms. Instead of simply writing recursive code, we should first analyze its computational cost. Through recurrence analysis, we can predict execution time, estimate memory usage, compare algorithm efficiency, design scalable software solutions. Today we explored hidden recursion costs, divide and conquer, chip and conquer, substitution method, tree method, master theorem, characteristic equations, famous recurrence sequences, and strategic selection of solving techniques. The key takeaway is that efficient programming begins with efficient analysis. Before implementing any recursive algorithm, always write its recurrence relation and solve it.